In this lesson, we are going to talk about arc length of a curve, and then we're also going to talk about finding the surface area of a volume of revolution. We're first going to start talking about arc length of a curve, and what I want you to imagine is when we're looking for arc length, we're looking for the distance traveled if you imagine that you're walking along a curve. So imagine this pink dot that I'm tracing. Imagine I'm walking along the curve and I want to find this distance. So from point A to point B. Now, in order to do that, we're going to build up a concept of breaking that interval A to B into small pieces and finding the length of the line segment between those 2 points when we break it up into intervals. So I want to find, for example, the line segment from here to here, whatever that length is. Then I want to find this length, then this length, etc. And then I want to add those all up, and that will give me an approximation of the length of this curve. However, that's just an approximation. So what we're going to do, like we did previously when we were trying to find the area under the curve, we're going to break up the intervals into smaller and smaller and smaller pieces until we get a limit that approaches the exact value of the arc length of that curve. So we're going to start by finding the length of these line segments, and then we're going to create those line segments so that they get smaller and smaller and smaller and add them all up. Now, in order to do that, I want you to imagine from this point here to this point here, we're basically looking at the hypotenuse of a triangle. So we have the change in x and then the change in y. And we're labeling this yi so that it mirrors and coordinates with the xi, this second point here. Okay, so now if I think about finding the length of just that one line segment by using Pythagorean theorem, I would have this side of the triangle squared plus this side of the triangle squared, and then I would take the square root. After doing some algebra manipulation, by multiplying both the top and the bottom on the inside of the triangle by delta x squared, I use some algebra manipulation, and what I end up with is this right here. So this represents the length of one of those line segments. Now, I want to add them all up, but I want to find the limit as x goes to infinity. We want to take an infinite number of intervals, which makes which makes those intervals get smaller and smaller and smaller. So that would be this here. And then using this idea, we can translate it into an integral. So to find the arc length on an interval from A to B, you would take the square root of 1 plus the derivative, and then you square it. So now that we've come up with this equation, let's define it officially. For the arc length of a function in terms of x, okay, we're going to say let f of x be a smooth function, meaning there's no points or cusps or asymptotes. We want to look at the smooth function over an interval from a to b. The arc length of the portion of the graph from a to b is given by this equation. So let's go on to our first example. So we have the graph f of x is equal to 2x to the 3 halves. We're going to calculate the arc length of the graph f of x over the interval from 0 to 1. So we're looking at it from here to here. We're trying to calculate this length. Round your answer to 3 decimal places. So here's the formula we just came up with for arc length. The first thing we need to do is find the derivative and square it. So I'm going to take the derivative of 2x to the 3 halves. When I do that, I get 3x to the 1 half, and then I'm going to square it to get the derivative squared. That gives me 9x. Okay, now I'm going to plug this into our formula. My point A and B, in this case, we're doing it on the interval from 0 to 1. I'm going to take the square root of 1 plus the derivative squared, so that's 9x, and then, of course, add in dx. In this example, we're going to have to use u substitution. So I let u be 1 plus 9x. So when I take the derivative, I get 9 dx. And then when I solve for dx, so I can substitute it, I get 1/9 du. So I'm going to replace dx with 1/9 du. 1 plus 9x is replaced with u. And I'm going to rewrite the square root as to the power of 1/2. So that way it makes it a little bit easier to integrate. We can use the power rule for that. Okay, when I integrate, I get 1/9 times the quantity of 2u 3 to the 3/2 over 3. Now, when I substitute for u, and I changed it as a function from x to u, I need to replace my limits, which now changed from 1 to 10. And when I do that, and I work out this arithmetic, I get 2.268 units. Now looking at a function with respect to y, instead of it having y equals f of x, we're looking at a function in terms of y. So it's going to be looking at a function x is equal to f of y, or in this case, they call it g of y. Okay, so here's our function. But because we're doing it with respect to y now, we're looking at our interval over the y-axis. So this would be our point C, and this is going to be our point D, from C to D. And the formula is going to remain the same. We're just going to change our limits and change the way we define our function. So our arc length formula, when we're doing this with respect to y, is going to be the integral from C to D, the square root of 1 plus the derivative of g of y squared dy. It says let g of y be equal to 3y to the third. We're going to calculate the arc length of the graph of g of y over the interval from 1 to 2. Now I want to point out that this was given to you in terms of y already. Keep in mind, if it asks you to integrate with respect to y, but the function is written with respect to x, you're going to have to rearrange the formula so that it is with respect to y. So make sure when you're actually plugging it into the formula that in the formula or in your function, it's all in terms of y if they're asking you to do this with respect to the y-axis. So here's our formula for arc length with respect to y. So the first thing we need to do is find the derivative of g and then square it. So my derivative of g of y is going to be 9y squared. That's here. And then when I square it, I get 81y to the fourth. So I'm going to set up my integral. So since we're going from 1 to 2, and this is telling us that it's over the interval 1 to 2. Remember, if you know that this is in terms of x, you're going to have to switch it so that it's in terms of y. So on the y-axis from 1 to 2, and then I'm going to write the square root of 1 plus, and then I'm going to plug in my value for my derivative squared, which we found was 81y to the fourth, and then of course put in the dy. Now, we haven't learned yet how to do this type of integral. I can't use u substitution in this case because of the 81y to the fourth. If I use u substitution, I don't have an x to the third in this formula anywhere to use for substitution. So in this particular case, you're going to use your calculator to find this value because we haven't covered how to do this yet. And when you use your calculator how to do that, you get 21.028 units. Now, if you're not sure how to use your calculator to find this value, let me walk you through how to do that. All right, so for those of you who do not know how to use your calculator to find this value, what you want to do is you want to go to the math button over here on the left side of your calculator, and then you want to scroll down. On mine it says option number 9, where it says FNINT for function integration. And then it will pop up where you can enter your values. So I'm going to put in 1 to 2. And inside here, I'm going to put my function. So I'm going to put in the square root of 1 plus 81. Now, we don't really have a y variable on here, so put it in as x, but just remember that this is in terms of y, but the variable that we're using on the calculator is x. I'm going to put in x to the 4th, and then, of course, dx. And when I hit enter, it's going to give me my value here. And the question said to round to 3 decimal places earlier. So we're going to round and make it 21.028, which is what we got here. In the second part of the lesson, we're going to talk about the area of a surface of revolution. And that's where we take this curve and we're going to revolve it around the x-axis to create this volume. Now, if we want to get just the surface area, when we break it into smaller pieces like this, and we're looking at the volume of it, what we're really looking at is we can approximate it with this red area of the cone. So if I imagine I turn this red area of the cone on its side, that's this slice right here. So what we're going to do is we're going to come up with those slices. We're going to add up the surface area of those slices, and then we're going to add them all up. And then we're going to take the limit as approaches infinity, where we take an infinite number of slices to get our exact value. So what I want you to imagine is we have this cone, and I want to look at just the lateral area of this red part of the cone here. And when I say lateral area, I mean to take the surface area but exclude the top and the bottom. We're just taking the surface area of the sides. And the formula for that is pi times r times L, where L is this distance from here to here. So we're going to use this, and we're going to use this cone to come up with a formula. Now, when I look at this picture here, it doesn't have a point to it. We're just looking at the red part. So I need to subtract off this pointed part here. We just want this slice here to use for our approximation. So what we're going to do is we're going to find the lateral surface area of the entire cone, which is the red and the blue together. And then I'm going to subtract off the lateral area of the smaller cone, which is just this tip, the blue. And what I'm going to have left is the lateral area of this red part here, which is what we want. We want to come up with a formula for that. So I'm going to call the lateral area of the lateral length here, this side length of the large cone L1, and then of the smaller cone L2. And the same thing goes for R1 and R2 for the radius. R1 will be for the big cone, and R2 will be the radius for the smaller cone. So I'm going to find the lateral surface area of the big cone, which will be this, and then I'm going to subtract the lateral area of the smaller cone, which is this. And when I use some algebra and clean it up, I get this. Now, from there, and you can read this in the textbook because it's fairly lengthy, but you're perfectly capable of reading this. There's a lot of algebra manipulation to get from this to this. And you will need to make sure that you rewrite this area here in terms of your function so that you can integrate. You integrate it over the interval from a to b using this formula. So again, of course, when you're looking to find your surface area, you're going to have to find the derivative of your function first and square it to plug it in here, and then you plug in your function here, and then you integrate. If you're doing it in terms of y, you get this formula here, where you go from C to D, where that's on your y-axis, And then, of course, your function is in terms of y. So let's look at our first example. So we're going to take the function f of x is equal to the square root of x over the interval from 1 to 4, and we're going to rotate it around the x-axis. So here's my function, square root of x, and we're going to do this from 1 to 4. So we're doing it in this area here where I'm coloring this blue. When we rotate that around the x-axis, we get this image right here. Now, if I want to find the surface area of that volume of revolution from 1 to 4, I want to make sure first so that I can plug it into my formula. Here's my formula. I want to find the derivative, and then I want to square it. So when I take the derivative of x to the 1/2, rewriting it in terms of an exponent rather than the root makes it easy, since you can just use the power rule. So then I take the derivative, and I have 1 over 2 times the square root of x. So then when I square it, I get 1 over 4x. Now, to make things easier, I multiplied my square root of x with the square root of 1 plus 1 over 4x. Since they're both the square root, I multiplied them together and got this. Then I found my u for my substitution. I'm letting everything underneath here be equal to u, so when I find du, I get 1 dx. So I can substitute du directly for dx. Now I still have my 2 pi here. This becomes u, so I can write it as u to the 1/2, and then of course du that I substituted for dx. And don't forget, when you change your variable like this, you have to change your limits. So I substituted 1 and 4 in for x and found what the value was in terms of u. So don't forget to do that. And then, of course, when I went through and did the arithmetic, and I evaluated that from 5 over 4 to 17 over 4, I got 30.846. And so whatever unit that would be in, it could be meters squared, it could be inches squared. This didn't indicate that here, but just keep in mind that this is a surface area, so this should be in some kind of unit squared. Okay, now we're going to do the same thing, but now we're doing it with respect to y. So I have this function here, 1/3 y cubed. And I'm going to spin it around the y-axis. And I want to do that from 0 to 2, so from here to here. When I spin it, get this solid of revolution here. And I want to find this solid of revolution. I want to find that surface area. I need to find my function, take the derivative, and then square it so I can put that in here. So my derivative would be y squared. And then when I square the derivative, I get y to the 4th. So that's what's going to go underneath my square root here. Okay, now we're doing this on the interval from 0 to 2, so I got to make sure I'm looking at the y-axis when I put in those limits, since we're doing this with respect to y. Here's my original function that I put in for f of x. Here's my derivative squared. To go to the next step, from here to here, I'm just cleaning it up a little bit. And then I'm going to say, let 1 plus y to the 4th be equal to u. And I'm going to figure out what I need to do to replace the y to the 3rd and the dy. I want to replace that. So when I solve this, when I take the derivative of u, I get 4y cubed dy. So when I solve this for y cubed dy, since that's what I want to replace, I get 1/4 du. So this and this gets replaced with 1/4 du. And so the 1/4 combined with the 2 pi over 3, that creates this pi over 6. Here's my u that I substituted. Here's my du. And then I had to change my limits in terms of u. Don't forget, since if I plug in 0 here to figure out I'm going from y to u. So I plug 0 in here, u would be 1. And then I do the same thing with 2. If I plug in 2 here, 2 to the 4th is 16 plus 1 is 17. So I got to change my limits in terms of u. And then I can go and start integrating, do my arithmetic, and I get 24.118.